10.6, the pH scale. So pH is used to measure the acidity of a solution. It's really measuring the hydrogen ion concentration. However, it's what's called a logarithmic scale. You saw those powers of 10 when we were talking about the water constant. And so it's a way to take those awkward powers of 10 and bring them down to just normal numbers. Or more usual numbers. Anyway, the pH of a solution is used to indicate whether it's acid or basic. For the most part, it ranges from 0 to 14. That 14 you'll recognize from the water constant that we have. The Kw is equal to 1 times 10 to the negative 14th. That negative 14th power there is where this 14 comes from. Acids are less than 7. Neutral is equal to 7. Bases are greater than 7. Of course, strong acids are smaller, lower numbers. Strong bases are higher numbers. Your weak ones are in the middle. There is also such a thing as watered down or dilute acids, strong acids, where they will not have very high, very extreme pHs. As a side note, acids are close to 0, between 0 and 7, bases 7 to 14. And the way I remember that is simply the numerical order is also the alphabetical order. It's sometimes weird to think about something that is very acidic has a 0 for the number. And so I just remember the ranges. I split at 7 and our plus or minus 7 from there, and it goes just A, B alphabetically. The pH can be used using a pH meter, which gives us exact numbers as you saw on the diagram on the first slide. We can also use indicators that change colors, and we talked about litmus and phenolphthalein previously. We can also use papers that are soaked in those and look at those colors as well. Usually the ones that are papers are soaked in a mixture of indicators. Different substances change their color at different pHs, and so we can have color changes at a range of pHs that can then give us it. Obviously, the meter is the only one that's going to give us a specific number and a very exact, precise answer, but still, it's the papers and indicator colors are usually more than good enough. Here are examples of each of those. I suppose I probably should have elaborated while looking at this one, but here it looks like this one has phenolphthalein indicator in it. Nope, it's got to be something else because it's a 4. Phenolphthalein is only pink in the presence of a base, so there's got to be something else. Probably litmus now I think about it. Maybe that is a red color. Anyway, here indicator paper changes color. Here other indicators change color. This one here happens to be red cabbage indicator, which you can make at home, although it smells. You got to boil the cabbage. Anyway, we go from very acidic to very basic here with neutral in the middle. This is a list of substances. If you want to take a look at it, it's in your book, or you can pause the slide here. I'm going to keep going. So with this, we're going to answer the questions here for practice. And so let's see here. HCl is going to be acidic. It's an acid, plus we have a very low pH here. Pancreatic fluid, 10 to the negative 8th. So this negative 8th here is going to be our pH, and so that's going to be a pH of 8, so that's going to be basic. It's awfully close to neutral. Sprite is going to be acidic. It's got a low pH. pH of 7 is neutral. Here, there is a number here before it, but usually the power of 10 is more than enough to figure it out. And so 10 to the negative 10 is going to be basic, and 10 to the, 10 to the negative 10 for the OH concentration. That would mean if we solve the problem that we had previously, the Kw is equal to concentration of H3O plus multiplied by the concentration of OH minus, and then we plug in the OH minus, this 10 to the negative 10 there, and we plug in the 1 times 10 to the negative 14th here and rearrange and solve. We're going to find that this thing gets approximately going to be a pH of 4-ish, or have a hydrogen ion concentration of times 10 to the negative 4. I'm just doing a very quick rough math in my head here, looking at the powers of 10 and kind of ignoring the numbers out in front, which is more than good enough for our purposes here. Anyway, 10 to the negative 4 is going to be a pH of around 4, which is going to make this one acidic. And then 10 to the negative 12 for the hydrogen ion concentration. That's a very small concentration, so that one is going to be basic. I believe the chart on the previous page had the powers of 10 as well, and so you could have just looked at those powers of 10. It's just that eventually you'll have to solve them mathematically, and this is how you would do it. Anyway, the pH scale, as I said already, is logarithmic. So the way that you actually calculate pH from a H3O plus concentration is to use a logarithm. I know many students in math have problems with logs, and so I just want to point out that a log is simply an operation. To me, it's no different than add, subtract, multiply, divide. It's just another thing where instead of choosing a symbol for it, we chose a word, and not only did we choose a word, we chose a multi-letter word for it. It would be almost like for addition, we just said add, or subtraction was sub, instead of having the plus and minus signs there. Anyway, what it does is it allows you to solve for powers, for exponents. So to calculate a pH, we simply take the H3O plus concentration and we plug that into here, and then it's just negative log of that on your calculator, and from there you'll get the pH itself. I will point out that if the number out here is 1, the pH is simply the power of 10 here, which I'm pretty sure is addressed on one of the upcoming slides. But this here is just a pH of 2, which I don't even have to do the math, because with this being a 1, it's just the power of 2 there. What the log base 10 does, as it says up there, is it gets rid of this 10, and then we're multiplying it by 1, so anything by 1 is itself. So it just ends up being that negative 2 there. Obviously, if it's a number out here in the front, you're going to have to use a calculator to figure it out, and that's okay. If you're given an OH concentration, you would have to use the water constant formula. The Kw is equal to concentration hydronium times concentration hydroxide, solve for the hydronium, and then plug the hydronium into this equation. In terms of sig figs here, the significant figures, we don't factor in the power of 10 here. The power of 10 here is what gives us the leading number, and so we use the whatever is before the power of 10, which this has 2 sig figs, and so this over here also has to have 2 sig figs. I know usually you're used to looking at this and saying this has 2, therefore this has to have 2, but this comes into play, this exact value here comes into play in the pH, and so because of that, it's not part of our sig figs out here in the decimal is. Anyway, here are some, you can see as pH decreases, the H3O plus is increasing. That is, we're getting more H3O plus in solution with the lower, smaller pHs. And that has to do with the neutral being 7, and so we're counting down on the scale for really acidic stuff, and down on the scale means more hydronium ion there in solution. Aspirin here, it asks us to solve for the pH of it, and so I'm just going to work that out here. I didn't copy the formula over already, so just as a reminder, pH is equal to the negative log of the H3O plus concentration, and so that is equal to the negative log of, in this case, 1.7 times 10 to the negative 3. Since there's a power of negative 3 there, I expect my pH to be around 3, but it's not going to be exactly, because that number in front isn't exactly 1. And so then plugging that into a calculator, negative log. Make sure when you do negative log that you actually use the negative sign and not the minus sign. Make sure you're typing in powers of 10 properly as well, and I get 2. It comes out 769, which is going to round off to 7. Again, 2 sig figs here, so 2 decimals there. This is exact, so it gives us that exact value there. And so we go from having 2 digits in our original to 3 digits in our answer here, pH of 2.77. Next, same kind of problem here. pH is equal to the negative log of the H3O plus concentration, which is equal to negative log of 4.0 times 10 to the negative 5th, and that is equal to, again, I expect something around 5. There we go. It is 4. That's going to be 40 is how it rounds out with our sig figs. We can also do the reverse process here. where you're given a pH and need to come up with the H3O plus concentration. You could undo the log. To be honest, I tend to just use this straight up formula here. There is a way to use powers of 10 to get rid of log base 10, but it's simpler just use this formula. The H3O plus concentration is equal to 10 to the negative pH, and so then you can just plug that into your calculator. You can even use the 10 to the X key if you have one on your calculator. Otherwise, you can type it in. It's not a problem. If this is a whole number for the H3O plus concentration, or excuse me, for the pH, then that is your answer, or you could write out 1 times 10 to that. But of course, those two are the same if you're multiplying by 1. If this is a decimal here, then you're going to get some specific number, and you'll need to write out that number in proper scientific notation. So for this one here, we're going to work it out. So H3O plus concentration is equal to 10 raised to the negative pH. For A, that is going to be simply 10 to the negative 3, or 1 times 10 to the negative 3. And on both of those, that is going to be, that's a 1. That is going to be molar, because we're talking about concentrations again. For the other one, we're going to do 10 raised to the negative 3.42. And so that we're going to have to plug into a calculator. So 10 to the X, negative 3.42. And I get a 3.8 times 10 to the negative 4 molar. And again, our sig figs are matching here, 2 here, which come from the decimals here. This one here, 1 here, so then only 1 here, which comes from the decimal part of this one. I'll let you pause and take a look at this chart if you want to, but you'll notice the H3O plus concentrations count from 0 to negative 14, while the OH does the reverse, negative 14 out to 0, and the pH scale matches the power, the exponent on the H3O plus scale. Of course, there are decimal numbers here in between these, which involve numbers in front of the power of 10 over on the H3O plus concentration.